Good afternoon, all. Welcome to the lecture of Advanced Discrete Mathematics. I'm audible? Okay. Okay. So in last lecture we have seen what is last point is nothing but the cut vertex. What should be a cut vertex? I think we have seen the definition in last lecture. If there is a vertex v small v in a graph G, then that corresponding vertex v is said to be a cut vertex of that graph. If yes, what is a cut vertex?
If we if we delete that vertex, then it disconnects the connected components of G.
It disconnects the connected any connected component of that corresponding graph G. That one is nothing but the cut vertex. Okay, and we have seen some examples on this. That is a cut vertex of a graph G. And if suppose there is a complete graph, is there is any vertex which is a cut vertex for a complete graph? Complete graph means it is a simple graph in which each pair of distinct vertices are joined by an edge. So tell me whether there is any vertex in a complete graph which is a cut vertex. Suppose we have K4 is there. That is V1, V2, V3 and V4 is there. V1, V2, V3 and V4. In this complete graph K4, is there is any vertex which is a cut vertex?
No, sir.
Same for all the corresponding our complete graphs. Okay, as K4 has no cut vertex, so from that one we can conclude that if there is a complete graph, then it has no cut vertex. Similarly, we can check for the K1, K2 also. As here there is K2 is a connected graph. As K2 is connected graph, the number of connected components in G will be 1. And whenever we will remove either an vertex V1 and or vertex V2, then the number of connected components in G minus V1 or G minus V2 is same as the number of connected components in G. So the corresponding any vertex is not a cut vertex of that K2 also. Same for remaining all the Kn. So if there is a complete graph, then it has no cut vertex. So no vertex of no vertex of complete graph is a cut vertex. It's a cut vertex. On the other hand, if suppose there is a path of length n, on the other hand, if Pn is the path of length n, where n must be greater equal by 3, where n must be greater equal by 3, then taking u and v be end vertices of this path to be the end vertices of Pn, end vertices of Pn, we see that every vertex v, every vertex, actually here we have taken u and v, let us take every vertex w apart from this u and v, apart from u and v is a cut vertex, whether this one is true or not. That is we have given if there is a path having length will be n and this n will be greater equal by 3 and u and v be its end vertices of that path pn, then each vertex w which is apart from the vertices u and v, it means w is a vertex which belonging to the path u and v, and as it is apart from u and v, it is neither u nor v, so such a w is nothing but a cut vertex, whether this one is true or not. What is a path first?
It is an open walk.
Then what is the difference between open walk and path if it is a open walk? Yes, obviously it is a open walk.
No vertex is repeated.
No vertex is repeated. So what is a path? Path is nothing but it is an open walk in which no vertex is repeated. It means each vertex in our walk will be distinct. So whenever we will remove one vertex W apart from this U and V, if we remove the end vertices of path, then there is no effect on its corresponding path. Just its length will be some decreased by 1, but there is no effect. Obviously, it is again a connected path only. Whenever we will remove either U or V. But if we remove any vertex W apart from this U and V, then obviously it disconnects that path.
Yes, sir.
So such a W is nothing but a cut vertex. So obviously it will be true. So that is, in other words, all but two vertices of Pn are cut vertices. Okay, all but two means except these two vertices U and V. Okay, these two vertices U and V are not the cut vertices, and remaining all the vertices which are belonging to this path U to V must be the cut vertices. Is it clear?
Yes, sir.
Now tell me why this n is greater equal by 3 only. n हा greater equal by 3 का घ्यायचा?
If we take n equal to 2 and if we remove that V vertex, then it will not disconnect the graph.
Disconnects. Same for the single vertex U also. Since whenever we'll remove that vertex only, then there is no vertex in corresponding G minus that vertex. So such a graph is not defined. Okay. So for that reason, here we have to take a n will be greater equal by 3. Yes. Up to now, any doubt?
No, sir.
Okay. Now there is one theorem depending on the definition of cut vertex. Let's see. See the statement. Let V be a cut vertex of the connected graph G. Sorry, let V be any vertex. Let V be any vertex of a connected graph G. Graph G. Then that V is a cut vertex if and only if, sorry, cut vertex of graph G, cut vertex of a graph G, if and only if there are two vertices U and W in G, vertices U and W of a graph G, both different from this V, both different from V, such that V is on every U to W path in graph G. So whatever we have given, there is one vertex V in the connected graph G. What is a graph? Graph G is a connected graph. Then that corresponding vertex V is a cut vertex of that graph G. If and only if there are two vertices U and W which are distinct from this vertex V, that is U is not equal to V and W is also not equal to V. Then every U to W path in graph G contains the vertex V. That is, it means whenever we will remove that V, then the corresponding graph G minus V disconnects. That is, we have to, as here if and only if statement, then again we have to prove this theorem in two parts. Okay. First part is only if part. In that, we have to assume that graph G is connected. That is already we have given, and we have to suppose that V is a cut vertex of a graph G. Let us suppose that. V be a cut vertex of graph G. As V is a cut vertex, then G minus V becomes a disconnected graph. Since G is a connected graph, what is the actual definition of cut vertex? Cut vertex means any vertex V is said to be a cut vertex of a graph G if it disconnects the any connected component of a graph G. But already we have graph G is connected. It means it disconnects G itself. Then G minus V becomes disconnected. It's a disconnected graph. Connected. And as graph G is a disconnected, it means it has at least two distinct components, that is distinct connected components. It means there is one vertex U which is belonging to first connected component and one vertex W which is belonging to second connected component. Is it clear?
Yes, sir.
So there are two vertices. There are two vertices U and W of G which lie in different components of G minus V. Which lie in different components of graph G minus V. As U and W are the two vertices which are belonging to two different components of V, G minus V, then tell me whether from that one we conclude that if there is a path from U to W in G, then it must include the vertex V.
Yes, sir.
So thus, although there is a path from U to W, as it is a connected graph, G is a connected graph, then each two vertices in graph G will be connected by a path. So thus, although there is a path from U to W in G, there is no path from U to W in G minus V. Since U and W are belonging to two different components of a graph G, it means there are at least two connected components. In one contains the vertex U and second one contains the vertex W. Okay. So from that one, we can conclude that if there is a path from vertex U to W in graph G, then it must include the vertex V. This implies that every path in G from vertex U to W contains the vertex V. And that is we have required. V as required. So first part will be proved. Okay? इथेपर्यंत कुणाला काही doubt?
No, sir.
If V is a cut vertex, then obviously G minus V is disconnected. Since G is a connected graph, then G minus V becomes a disconnected graph. As it is a disconnected graph, it means there are at least two components in G minus V. Then only we can say that the corresponding G minus V is disconnected. It means there must be exist two vertices U and W in graph G which are belonging to two different components in graph G minus V. So as graph G is connected, then obviously for each pair of vertices U and W of G, there must be a path between them. But as G minus V is disconnected and U and W are belonging to two distinct components, then there is no path from U to W in graph G minus V. And from that one, we can conclude that if there is a path from U to W in graph G, then that must contain an vertex V. And that is we have to prove. Okay, so first part will be proved. Now the second part. In second part, we have to assume that every U to W path in G contains an vertex V, and from that one we have to prove that the vertex V is a cut vertex. So only if part, suppose that U and W are two vertices of G, or two vertices of a graph G different from vertex V, such that every u to w path in G, every path in G contains the vertex V, contains V. Okay, and we have to prove that V is a cut vertex. As each path from vertex U to W in a graph G contains an vertex V, and by definition of path, we know that each vertex of that path will be distinct, and we have seen after the definition of cut vertex, if there is a path of length n will be greater or equal by 3. Here u and w are the two vertices. V is a vertex which is different from that two vertices u and w. It means here there is a path having length will be greater or equal by 3. So by the definition of that is the Pn, then we must, whenever we will remove the vertex V, as we know that if there is a path Pn having length will be greater or equal by 3, then each vertex of that Pn is a cut vertex except the end vertices. Here end vertices are u and w. V is a vertex which is belonging to this path u to w. Then that V must be a cut vertex.
Yes, sir.
So V is a cut vertex, and that is we have to. Okay, and hence the yes, Kunal ka hit out यामध्ये.
No, sir.
Okay. One more theorem is there. Let G be a graph with n vertices. Let G be a graph with n vertices where n is greater or equal by 2. It means it contains at least two vertices. Then G has at least two vertices, at least two vertices which are not the cut vertices. Not the Okay, if there is a graph with n vertices where n is greater or equal by 2, that is, it contains at least two vertices. Then from that one, we have to prove that that graph G has at least two vertices which are not the cut vertices. Okay. So actually, we have to prove there is a graph in which, if there is a graph with n vertices where n is greater or equal by 2, then we have to prove that that graph G has at least two vertices which are not the cut vertices. So here we will assume the contradiction, that is, the graph G has at most one vertex which is a cut vertex. Okay, actually we have to prove that at least two vertices which are not the cut vertices, but here we will assume its contradiction, that is, graph G has at most one vertex which is a cut vertex, and from that one we will get somewhere contradiction, and from that one contradiction from that contradiction we will conclude that the corresponding graph G has at least two vertices which are not the cut vertices. Okay, so we will prove this result by using the contradiction. So prove clearly. Now again here, graph G is a graph, given that G is a graph with n vertices only, whatever, whether this G is a connected or disconnected. If suppose graph G is a connected, if graph G is connected, then we will prove that the corresponding graph G has at least two vertices which are not the cut vertices. If suppose G is not a connected graph, G is not connected, it means it can be expressed as a distinct union of connected components. Then each connected component has at least two vertices which are not the cut vertices. So obviously the result will be true for disconnected graph also.
Yes, sir.
So here just we will prove for the connected graph only, and from that one the result will be obviously true for disconnected one also. Okay, so let G be a connected graph. Be a connected graph. Okay. Now let us assume the result is false. Result is false for graph G. For our graph G. And so the proof will become complete if we get a contradiction somewhere. Complete if we derive the contradiction from this one, from this. Okay. So as here we have assumed that the result is first, it means the graph G has at most one vertex, which is a cut vertex. Okay. Thus we are assuming that we are assuming that graph G has graph G has at most one vertex, at most one vertex, which is cut vertex, which is cut vertex. As already we have given that graph G is a graph with at least two vertices, since n is greater or equal by 2. So let us suppose that U and V be any two distinct vertices of a graph G. As U and V are any two distinct vertices of a graph G, then we will suppose that the distance between U and V becomes the largest distance between U and, that is the largest distance between the any two vertices in a graph G. Okay. Now let U and V be vertices in G, be vertices in G such that the distance between U and V, the distance, that is d of UV between them, is the largest distance. Is the largest distance between any two vertices of a graph G. Largest distance between any pair of vertices, in graph G, vertices in graph G, whether such two vertices will be exist or not. असे दोन वर्टेक्स नक्की मिळतील ना, कारण ग्राफ जी माझा कनेक्टेड आहे. ग्राफ जी जर कनेक्टेड असेल तर मला कमीत कमी त्यामध्ये दोन वर्टेक्स मिळू शकतात ज्यांचा डिस्टन्स हा दुसऱ्या कोणत्याही दोन वर्टेक्सच्या डिस्टन्स पेक्षा लार्जेस्ट असू शकतो. इट मीन्स बाय द डेफिनेशन ऑफ डायमीटर रेडियस there must exist such type of vertices U and V. As distance between UV is the largest distance between any pair of vertices in G, then what is this one? Whether this one is a diameter or radius?
Diameter.
That is, distance between U and V is nothing but the diameter of graph G. Okay, which is just by the definition of diameter of graph G. And as graph G is connected, then such two vertex must be exist. Now, as G is connected, since we have assumed that G is a connected graph, G is connected, and has at least two vertices. At least two vertices U and V, where U is not equal to V. Thus, by our assumption, what should be our assumption? That is, there is one vertex which is a cut vertex. One of these vertex must be a cut vertex. Say V be a cut vertex. Since U and V are any two distinct vertices in a graph G, and we have already supposed that there is the graph G has at most one vertex which is a cut vertex. We have supposed that that vertex is nothing but V. That is, V is a cut vertex of a graph G. Then by definition of cut vertex, whenever we will remove an vertex V from a graph G, then G minus V becomes disconnected. Then G minus V becomes disconnected. It means G minus V becomes disconnected. It implies that there are two vertices U and W which are belonging to two distinct components of G minus V. Is it clear?
Yes, sir.
So there is a vertex W in graph G, W in graph G, which does not belong to, does not belong to the same component in which the vertex U is there. Same component as U does in G minus V. G minus V. Since V is a cut vertex, it means for each path U to W in graph G, the vertex V is there. So from that one we conclude that U and W are the two vertices which are belonging to two distinct components in G minus V. Okay, this implies that every U to W path in graph G contains the vertex V. Contains the vertex V. Okay. So it follows from this that the shortest distance between, that is shortest path between U to W contains the path U to V.
Yes,
As
sir.
V is belonging to every U to W path, then the shortest path from U to W contains the shortest path from U to V also, since V is belonging to each path U to W. So the shortest path from U to W, from U to W contains the shortest path from U to V. Shortest path from U to V. Now tell me whether this one is possible. It means here are two vertices U and W having path length is greater than this path length of U to V. Yes, na? As V is belonging to every U to W path. Then which path have largest length? U to W or U
U
to
to
V?
W.
Obviously, U to W has a path length must be greater than path from U to V. But we have assumed that is our supposition is that distance between UV is nothing but the largest distance between any pair of vertices in graph G. But here we will get the vertex U and vertices U and W having path length is greater equal by path length from U to V. So this one is not possible, since we have already supposed that U and V are the any two vertices having path length will be greater than all the remaining vertices in graph G. But here we will get the vertices U and W, that is the path from vertex U to W which contains the path from U to V. But this one is not possible, and this contradiction arises due to our wrong assumption. Which assumption will be wrong?
At most one vertex is
That is, there is at most one vertex which is a cut vertex. So what should be the correct statement?
at least two.
At least two vertices which are the cut vertices. So our assumption is wrong. Assumption is wrong. So G has at least two vertices, which are cut vertices. Vertices which are cut vertices in graph G. Cut vertices. And that is we have to prove. Here we will prove this result. We have proved this result by graph G. That is connected graph G. If graph G is a disconnected graph, then this we can prove this for each connected component of that G. As it is true for each connected component, then obviously it is true for the graph G also. Yes?
Yes, sir.
Okay. So hence the yes, यामध्ये कुणाला काही डाऊट?
No, sir.
Okay. Now, next there is one definition, that is a connectivity, which is also called as a vertex connectivity. Connectivity. Okay. That is, it is nothing but vertex connectivity also. See definition first. Let G be a simple graph. Let G be a simple graph. The connectivity of that simple graph G, the connectivity of a graph G denoted by small k of G is the smallest number of vertices is the smallest number of vertices in graph G whose whose deletion disconnects sorry deletion from G whose deletion from graph G, that is deletion from G, gives either a disconnected graph either a disconnected graph or graph K1. What is K1?
Complete graph with vertex 1.
Complete graph with vertex 1. Okay, if there is a simple graph G, then the connectivity of that simple graph G is nothing but K of G, and it is nothing but the smallest number of vertices whose deletion from graph G gives either a disconnected graph or the graph which is nothing but the complete graph K1. Okay, see some examples. Consider this is a graph G1, G2, and G3. Okay, so these are the three examples. Now, tell me, what should be the connectivity of graph G? G1?
2.
Connectivity of graph G1 is equal to T. Since if we have to disconnect that graph G1, then we have to remove at least two vertices. For example, tell me any two vertices for graph G1.
V2, V6.
V2 and V6. Whenever we will remove the vertices V2 and V6, then we have to remove all the vertices which are incident on the vertices V6 and V2. That is this one, and this one. Same for V2 also. This one, this one. So here we will get two components. In one, there is only vertex V1, and second component contains vertex V3, V4, and V5. Okay. So from that one, we conclude that connectivity of graph G1 will be 2. Is there are any vertices other than this V6 and V2 having deletion disconnects the graph G1?
V5 and V3.
V5 and V3. Except these V5 and V3?
No, sir.
Whenever we will remove V5 and V2, whether the corresponding graph is disconnected or not?
Yes, sir.
So obviously, the connectivity of G1 will be 2. Okay. Since here actually we have to find out the smallest number of vertices. Whenever we will remove the 3 vertices, then also the corresponding graph will be disconnected. But actually, what is the connectivity? Here we have to find out the smallest number of vertices having deletion disconnects the graph, or it is K1. Okay. Now tell me, what is the connectivity of G2? What is the
3.
connectivity of which are those vertices?
V1, V2, V4.
First tell me, what is the connectivity of a graph G? Yes, what is connectivity?
3, sir.
कनेक्टिव्हिटीच्या डेफिनेशन मध्ये काय दिलं आहे ते पहिला लक्षात ठेवा. जी बी अ सिंपल ग्राफ. वेदर
Simple graph.
ग्राफ इज अ सिंपल ग्राफ.
No, sir.
No,
सो
sir.
दिस इथं अप्लायच करू शकत नाही आपण, हा ना. ग्राफ सिंपल असेल तर त्या गोष्टी बघायच्या आहेत. हा ग्राफ सिंपल आहे का? हियर देयर आर 2 vertices from vertex
No, sir.
V3. Okay. Now tell me, what is the connectivity of this G3?
Two, sir.
Which are those vertices?
V1, V3 or V2, V4.
Whenever we will remove V1 and V3, then which are those vertices, edges which are we have to remove? That is this one, this one, this one, this one, this one, this one. Now tell me, what should be the connectivity of graph G3? Sorry, number of connected components in graph G3. 1, as G3 is connected.
Yes, sir.
So whenever we will remove V1 and V3, whether it disconnects the graph, there must be an edge from vertex V2 to V4.
Yes, sir.
So again, the connectivity of G3 minus, that's it, V1, V3 is nothing but 1. But what is the definition of connectivity? There is a simple graph G, then we have any vertex connectivity of graph G is nothing but K of G, and that one is nothing but the smallest number of vertices which disconnects the graph G, that or it is equal to K1. Obviously here there are 2 vertices V2 and V4, then it implies that that one is not equal to K1.
Yes, sir.
K1 ला ही इक्वल नाही, डिस्कनेक्ट ही करत नाही, तर ते वर्टायसेस माझी कनेक्टिव्हिटी 2 कशी होईल? हा ना.
3 L, sir.
Yes, whenever we will remove 3 vertices, if suppose we will remove V1, V2 and V3, again these edges vertices are, that is all those edges which are incident on V2 we have to remove. So there is only one vertex V4 in G3 minus V1, V2, V3, that is equal to K1. Yes?
Yes, sir.
So the connectivity of G3 is nothing but, okay. So from that one we conclude that for n greater or equal by 3, for n greater or equal by 2 actually, since here we will take 1, then it is obviously equal to K1 only. So for n greater or equal by 2, the deletion of any vertex from graph Kn, that is complete graph Kn, results in Kn minus of 1, since here we have removed a single vertex. Okay, so same for if suppose we have removed t vertices from the graph Kn, then and in general the deletion of t vertices where t is less than n, where this t is less than n, since complete graph Kn has n vertices, results in Kn minus t, results in Kn minus of t. So if there is a connected graph, that is complete graph Kn is there, then what should be the connectivity of that Kn? Here we have seen for the K4. What should be the connectivity of K4? Actually, this one is K4, na? Complete graph K4. G3 is nothing but K4. So the connectivity of Kn is nothing but connectivity of Kn. That is K of Kn is equal to. What is the complete graph? Complete graph is nothing but it is a simple graph in which each pair of distinct vertices are joined by an edge. म्हणजे मी एक दोन वर्टेक्स जर एखाद्या n ग्रेटर इक्वल बाय 2 मधून जर एखाद्या दुसरं वर्टेक्स जर रिमूव्ह केलं तर तो ग्राफ कधीही डिस्कनेक्ट होणार नाही. त्याला एकच पॉसिबिलिटी आहे ते म्हणजे ती K1 येण्यासाठी. आणखी K1 येण्यासाठी मला n मधून किती वर्टेक्स रिमूव्ह करावे लागतील? n वर्टेक्स आहे त्यात एकच वर्टेक्स K1 म्हणजे काय सिंगल वर्टेक्स राहील ना काय तर ग्राफ जी मध्ये एकच वर्टेक्स राहील कुठेतरी. मग n वर्टेक्स असतील तर मला एकच वर्टेक्स ठेवायचं असतील तर रिमेनिंग किती वर्टेक्स मला काढून टाकावं लागतील?
n minus n minus 1.
Then obviously the connectivity of that complete graph Kn is n minus 1. Yes or no?
Yes, sir.
It is also easy to see that it is also easy to see that a connected graph G has connectivity one if and only if either G is nothing but K2 or G has a cut vertex. G has a cut vertex. Is it clear? If there is a connected graph G, then it has a connectivity 1 if and only if either G is equal to K2 or it has a cut vertex. Since what is a connectivity? If there is a simple graph G, then connectivity of that graph G is nothing but the smallest number of vertices having deletion either disconnects the graph or it is equal to K1. If G is equal to K2, it means there are only two vertices V1 and V2. Then removal of any vertex from that K2, it does not disconnect the graph G, but it is equal to K1. Yes?
Yes, sir.
Or if G is not equal to K2, then that graph G must has a cut vertex. Then only we say that the given graph G has a connectivity 1. एकच वर्टेक्स माझा जर रिमूव्ह केला तरच मला कनेक्टिव्हिटी 1 येईल ना. तर त्या केससाठी मला काय असला पाहिजे? कट वर्टेक्स असला पाहिजे. हे दोनच पॉसिबिलिटी आहेत एखाद्या कनेक्टेड ग्राफची कनेक्टिव्हिटी जर 1 असेल तर. मोरेवर connectivity of a graph G is equal to 0 if and only if G is equal to K1 or already our graph G is disconnected. करेक्ट आहे का हे?
Yes, sir.
जर ऑलरेडी ग्राफ माझा डिस्कनेक्टेड असेल तर परत डिस्कनेक्ट करायची गरजच नाही ना. कनेक्टिव्हिटी म्हणजे काय? स्मॉलेस्ट नंबर ऑफ वर्टिसेस हॅव्हिंग डिलीशन डिस्कनेक्ट्स द ग्राफ G or it is equal to K1. If G is K1, then also we have a connectivity 0. But if suppose G is not K1, then connectivity of that corresponding graph G is 0 if and only if the graph G is disconnected. जर ग्राफ G डिस्कनेक्टेड नसेल आणखी तो K1 ही नसेल तर माझी कनेक्टिव्हिटी 0 येणं पॉसिबलच नाही. करेक्ट आहे?
Yes, sir.
Okay. Now again one more definition is there. A simple graph G is called n connected where n is greater equal by 1 if and only if connectivity of G is greater equal by n. Okay, so any simple graph G is called n connected if its connectivity will be greater equal by n. Okay, now we have one note. Let U and V be any two vertices of graph G let U and V be any two vertices of graph G, any two vertices of a graph G, then a of collection, actually what is a collection? C, P, actually it is a collection of path P1, P2 to so on Pn. That is there. It is a collection of Pn path from vertex U to V in graph G of U to V path, and is said to be internally internally disjoint if given any two distinct pairs, that is paths Pi and Pj, which have only two vertices common, which are nothing but U and V. In the collection U and V are the only vertices in which Pi and Pj having common. Okay, what is this note actually? If there are two vertices U and V in a graph G, and if suppose there are n path, that is a collection, that is, it is a set which is a collection of n path from vertex U to V, which is denoted by P1, P2 up to so on Pn. Then these n paths are said to be internally disjoint if given any two distinct pairs Pi and Pj in the collection. Then U and V are the only vertices in which that is from Pi and Pj have common. It means if we take any two paths from that n path, then U and V are the only two vertices which are common in these two paths, and all the remaining vertices must be distinct. Okay? कळती का ही नोट?
Yes, sir.
कोणतेही दोन पाथ घेतले तर त्या दोन पाथ मध्ये फक्त U आणि V जे एंड आहेत ते सेम आले पाहिजे. मधील जे काही वर्टेक्स असतील ते डिस्टिंक्ट असतील. क्लियर आहे?
Yes, sir.
Now there are some note for tree. Now tell me whether tree is a simple graph, multi-graph or pseudo-graph.
Simple graph.
Obviously every tree is a simple graph. Every tree is a simple graph. Can we give one example of tree in which there is one isolated vertex? What is isolated vertex?
Which has degree 0.
Which has degree 0. Is there is any vertex in tree having degree will be 0?
K1.
K1 is a graph having degree 0, except this K1. What is a tree first?
It is complete acyclic.
Connected
acyclic
graph. Na? If there is a graph other than this K1, then the degree of any vertex will be 0 if and only if that graph will be disconnected only. Na?
Yes, sir.
And such a graph is not possible. Such a graph is never a tree. It means there is no vertex that is except this graph in which there is an isolated vertex in that corresponding tree. Now if suppose there is a tree, okay, and if we add one edge in that tree, then whether corresponding graph again tree or not?
No, sir.
Obviously there must be one cycle in that corresponding graph, new graph, that is whenever we will add one edge in that tree. So addition of any new age in tree contains exactly one cycle. Contains exactly one cycle. Okay. The deletion of any age from tree, is there is any effect on that tree?
No, sir.
Actually, we have proved one result. If there is a tree, then each age of that tree is a bridge. What is a bridge? Any age is said to be a bridge if removal of that age disconnects that graph G. Yes, na?
Yes,
Any
sir.
age E of a graph G is said to be a bridge if G minus V is a disconnected graph. Okay. So if there is a tree, then removal of any age from that tree must disconnect tree, since each age of a tree is a bridge. That one is one theorem. Okay. So removal of the deletion of any age, the deletion of any age from a tree from a tree disconnects the tree. Disconnects. And last one is nothing but every tree is a bipartite graph. Every tree is a bipartite graph. That is, here it is possible to write graph. Here it is possible to divide the vertex set of graph into non-empty sets such that vertex set, that is, there is no vertex common between these two vertices, and each edge has first one end vertex in first vertex set and second end vertex in second end is in second vertex set. Okay, so these are the some important note on. Yes, आतापर्यंत कुणाला काही डाऊट?
No, sir.
Actually, there is one note. That one is nothing but a tree does not contain a isolated vertex, but there is one graph K1, which is a tree, and here there is a vertex which is an isolated vertex. So if we have to write that note, then we have to mention the graph must be distinct from this K1. Okay. Yes.